Think of a tree that you might find in nature. If you look at the branches of that tree, do those branches loop back on themselves? Probably not. Same thing here in the network with a spanning tree. A spanning tree is a topology that is loop-free. We're not going to have branches looping back on themselves. And if you also consider that tree in nature, at the base of the tree we have a root system. Same thing here, we have a root bridge out of which this spanning tree topology is radiating. And we want to be able administratively to determine and influence which switch is acting as the root bridge. If we just plug a bunch of switches together, and I've seen this happen, we might have a suboptimal path. We might be forcing traffic to flow through a really old 10 meg switch as an example. We don't want to let spanning tree just happen. We want to influence it. And to do that, we need to be able to look at a topology and determine right now who is the root bridge and which of these ports are forwarding and which of these ports are blocking. After all, if every port was forwarding, that could cause that layer 2 topological loop that we don't want. The first question that we ask is, who is the root bridge? What is the base of this spanning tree? And the root bridge is a single bridge or switch in our networks in a spanning tree topology that has the lowest bid. It has the lowest bridge ID. The bridge ID is made up of a bridge priority that we can administratively configure and a MAC address. By default on our Cisco Catalyst switches have a default priority of 32.768. And if we just leave them at their default priorities, then the MAC address becomes the tiebreaker. Whichever switch has the lowest MAC address becomes the root bridge. Let's take a look at this topology on screen. These are actual MAC addresses from a topology that I have set up right now. And both switches, switch A and switch B, they both have their default priorities of 32.768. And the first question we want to ask is, who is the root bridge? Since the priorities are a tie, we need to look to the MAC address to see who's the root bridge. If we look at the first 3 hexadecimal digits of each switch, I think we can figure it out. Switch A has 001 as its first 3 hexadecimal digits in its MAC address. Switch B has 000. That's lower than 001, so that means switch B is going to be our root bridge. Great, now we know that this is the base of our spanning tree. However, we do not yet know which ports are forwarding traffic and which ports might be blocking traffic. We need to define the different port states. First of all, let's take a look at the root port. A root port is a port on a non-root bridge. Switch B is our root bridge. It will have 0 root ports. Switch A, however, is a non-root bridge. It will have 1 and only 1 root port, and it's the port that's closest to the root bridge in terms of cost. And cost, by default, is dependent on the interface speeds. Notice that switch A has a couple of paths to get back to switch B. The top path, the top network segment, is running at 100 megabits per second, and as you can see from the table on screen, that has an STP port cost of 19. The bottom path, network segment 2, it's running at 10 megabits per second. That has a cost of 100. 19 is less than 100. That means it's less costly for switch A to get to switch B if it goes out of fast Ethernet 1/0/1. It's a cost of 19 as opposed to a cost of 100. So fast Ethernet 1/0/1 on switch A, that becomes our root port. Next, we ask, who are the designated ports? And a designated port exists on every network segment. It's the port on a segment that's closest to the root bridge in terms of cost. And here we have a very basic topology. We only have 2 switches, so it's going to be very easy to figure out who the designated ports are because we cannot get closer to the root bridge than on the root bridge. In this case, both network segment 1 and network segment 2, the ports on those segments that are closest to the root bridge are the ports on the root bridge. Gigabit 0/9 on switch B and gigabit 0/10 on switch B. And we look around at any port that is left in our topology. Fast Ethernet 1/0/2 on switch A in our case. If it's not a disabled port, in other words, if it's not administratively down, and it's not, that means that it is a non-designated port, which means it's blocking traffic. This is giving us our loop-free topology. We're not going to have a loop because production traffic is not going to be flowing into or out of Fast Ethernet 1/0/2 on switch A.